Okay, it's lecture 20 of our computational microelectronics 2024, and let's go to our lecture material directly. So today we will talk about method called as level set. So I think that maybe we can spend 2 lecture hours for this topic. So let's just get started. So up to now we have thought about the device simulation. Now you can perform the device simulation for one-dimensional p-n junction, and also can perform additional transient simulation and a small signal analysis. All of them were related to the device simulation, and now let's come back to our the initial interest on the process simulation. So let's consider a certain process called as etching. So etching means that if we wanted to make a certain pattern on the silicon wafer, we adopt this etching process. By etching process, initially flat surface can be now turned into the surface with a certain pattern here, and this part is of course the part of silicon or other material was etched out, and now we have a certain pattern. So actually when we consider the etching process or all kinds of other processes, so actually there are many various physical scales. So it seems that certain meter scale or micrometer scale or something like that. Let's just think about clean room. So in this clean room we have a facility. Yes, so inside this machine, so wafer is being etched. In this case actually the size is meter scale. However, how can we actually etch a certain wafer? So although here we have a thin wafer here, in order to make a certain etched pattern, we need some physical object to make an actual etching process. So for example, if we consider plasma etching, then we need plasma. So size of plasma, so physical size, is not like this one. This is just 600 micrometer, and our plasma gas has a much larger size here. And in this case also we can make some consideration the interface between our wafer and plasma. So this is the one we are now talking about. So here we have plasma, and here we have a vapor, and in between them something happens. However, usually this is not the size of our interest. Okay, so because this is too huge, and this one doesn't consider the details of our patterning. Actually what we wanted to do is what is the actual size of this whole etch hole made by etch process. This kind of information is really important for our later use. So instead of this clean room scale or plasma scale, we are more or less interested with feature scale. Here feature means that the size of etched pattern. So if we perform, for example, 10-minute long etching process, then how deep will be the hole and how wide the hole. So that is answered by this feature scale simulation. Okay? And of course, in reality, so ions are coming into the hole, already existing holes, and there will be certain chemical interaction between this silicon vapor and ions etchant. So we have to consider actually atomic scale interaction. But in this case, the atomic scale interaction is just a nanometer scale, but we wanted to make a hole whose depth is several micrometer or something like that. So this is in the atomic scale. The physical size is too small, and also the reaction time is too short. Although we are considering minutes or second level of process time and size of micrometer scale feature in this simulation, but atomic scale consideration just shows a small part of the entire system. We can never perform atomistic scale simulation for feature scale. So usually this atomic scale is just used for a reduced small system, and from this small system we get some information, and that information is transferred to this feature scale simulation. So how frequently this reaction occurs, that information is obtained from atomistic simulation, and that is used for our usual feature scale simulations. Okay, but today what I wanted to say is not this very rigorous simulation. So first of all, let's think about feature scale. So here feature scale here means that the size of actual pattern we wanted to see. So not the pattern in our facility or plasma or atomic scale, but the one we wanted to have on the wafer. So in this case, for example, here we are looking at certain profile of etching time. Here we have different etching time. So within short time we have a relatively shallow hole, and if we keep etching, actually now we can find that the etch depth is increasing. But you can immediately understand, although we have increase of the same amount of time scale, but in this case the increase is relatively large and increase is not that large, so it is getting saturated. So of course, in order to make our desired pattern precisely, we must be careful about simulating this one. Point is, in order to make such kind of etching process, always the shape of our structure is changing. For example, this was the initial one. After that, now we have a change of structure. For example, let's consider a point here. Previously, it was belonging to the silicon resin, and now the same point should be regarded as what? Should be regarded as just a gas phase. So in order to make this kind of etching process, actually we have to consider the change of boundary. Its shape changing is the most important one we have to carefully consider. So how can we consider this kind of things? It is not that easy. So the best way and most expensive way would be just to make so many grids, and if a certain etching occurs, actually we can just flip the material index from silicon into a gas phase. Then that is corresponding to the etching of that small volume. So that can be done in voxel like approaches. However, think about this one. this one really requires so large space. So if we wanted to make a certain grid, then we have to have many grids and assign them as, okay, you are silicon, you are a gas, and you are silicon. So in order to precisely represent this shape, actually all over our points should be placed quite densely. Let's think about this one. If we have this kind of a description, then the best thing we can expect is, okay, this is silicon, and this is gas and gas. So what we can have is just this one. This is the minimum size we can have, and actually if we have a little bit wavy shape, then can we expect we can make a good enough description about this wavy shape? So actually not if this wave is strong enough. Even when we have this wavy shape, then what we can have is just fully discretized version. One voxel up or one voxel down. So what we can say is just a discretized version of this description. But so yes, if we adopt this one, then the size of this how can I say certain change shape is nanometer scale, and we need micrometer scale size. So if we consider three-dimensional feature, that will make quite a large system. So that introduces much problems in our description. So in this paper or in this slide, I'm just showing that moving boundary is really an important issue of our process simulation or emulation, because during the process always the shape of our system is changing, so we need to okay, so I think that so our live stream is not that smooth. So previous a few seconds ago it was disrupted, but I hope that now it is recovered and working properly. Okay, so once again we must be careful about describing the shape, because if we introduce a certain regular grid, then it is okay because it doesn't change. Although shape is changing, the boundary is moving, however, we can have well-defined static mesh. Then the disadvantage is the resolution should be quite fine, so that will introduce some problems. On the other hand, what we can do is, instead of that, for each time instance, we can make another mesh description. So if we have this kind of a little bit curved space, well, why don't you just express it with this curved space? So we can introduce many triangles, and as we do usually, we can make good description about this shape at a certain time instance. Point is, when the shape is now changing, what we have to do is now remesh the new structure. If the structure is now changing, then now we introduce a different quantities, and also since meshes are different, our previous information should be transferred to the new mesh also. That introduces certain problems. Of course, I think that although I'm talking about or I'm complaining about difficulties of this process simulation for moving boundary, but actually we can do if we spend considerable amount of computational effort, then actually we can do. But point is, what we can do or what we wanted to do is efficient estimation about the final shape of our structure. So for that purpose, for efficiency, so we are now introducing level set method. In this level set method, so think about this one. If we have a certain shape, certain bias, boundary we wanted to describe, what we do usually is like this. Okay, introduce some points along the boundary, surface boundary, so we can do it, and also introduce some internal points. So just to introduce certain elements corresponding to this set of elements. So now you can easily understand this is a very efficient way or a general way we can discretize our simulation domain. So that is what we do in most cases, and especially in the case of device simulation, we wanted to have this kind of discretized mesh. But in the case of level set method, we don't want to the exact point corresponding to the boundary. So instead, we wanted to introduce a certain function called as a level, and when this function, level function, becomes 0, then that point is defined as the boundary point. So that is the point. So simply speaking, in this description, we don't introduce a mesh attached or mesh particularly fitted to this shape. So instead, we just introduce regular mesh with usually uniform spacing, and on this regular mesh we introduce a certain level function, and if this level function has the value, for example, value corresponding to 0, then this point is detected or regarded as a boundary point. So now think about this one. If we have, for example, let's think about this one. Here we have level function corresponding to 0.5. Okay, and in this point we have level function corresponding to minus 0.5. Then none of them corresponding to a boundary. Then how can you find the actual boundary? Because we will take the linear approximation in this on this edge. So the value, level value, is linearly changing from 0.5 to minus 0.5. So we can easily understand at the middle of this journey we have the value corresponding to the boundary. So if we have to have just regular mesh, rectangular mesh, uniform rectangular mesh. So in order to introduce or describe this shape, actually we have to introduce also certain line corresponding to this intersection point. Otherwise, we will just lose the resolution. However, right now, we are now introducing certain level function, and actual boundary is determined by interpolation between two level values. So even without introducing quite a fine rectangular grid, we can get so better resolution than just normal rectangular grid. So that is the point. So in this case, advantage is now this is static. So although shape is changing, but our mesh structure is just homogeneously, uniformly placed rectangular one, and also we can introduce a fine resolution, or so okay, we can describe small features with this one. Of course, it is not it cannot be applied every case, but within certain reasonable restriction, we can use this level-sum method. So today we will just consider level-sum method, and using this level-sum method, there is a kind of practices corresponding called as process emulation. Here I have introduced a certain quotation mark for this emulation. Emulation here means that we don't care about detailed physical mechanisms to actually make this kind of etching process. As we have seen in our previous slide, actually the change of shape in this feature scale is always related with physical mechanism happening in the atomistic scale. However, in this process, so-called process emulation, usually we don't care about the much detail of that one, just to trace change of boundaries. So by using this technique, actually we can make certain simulation tool or emulation tool for investigating the process simulation steps. So it is quite useful in our case. So today let's just make a real simple example on this one. So since today is devoted to the first part of this level set discussion, I wanted to start from the very beginning. So in this slide, we are now talking about how can we load an initial structure. For example, let's prepare a set of points. So this is x, y, and a pair of coordinates, and each line is corresponding to a point or vertex, and this is list of them. But appearance order is quite important in this case. So starting from point 1 comma point 1, so starting point start from this one, we read the next line. It is corresponding to 13.6 0.1, so this is corresponding to that line, and we draw on line segment here, okay, starting from here, and we go to this one. And how about the next one? Next one we have this, and next. If we go this way, then the final pair is corresponding to this one. Here we have 13.6 comma 5.1, and the last point is corresponding to 0.1 comma 5.1. So we have the final line segment here, and now we have the last point. And since we are just talking about not just a line but certain boundary surface, so it is implicitly assumed that, okay, this last point is actually connected to the first point. So although we don't have something like 0.1, 0.1, but it is assumed that the last one is connected to the first one, so we will have this kind of behavior. So please note that when you visualize these lines, you can find that their directions are, or they are rotating in the counterclockwise. So counterclockwise description is shown. Of course, we can think about many different cases. Although we have considered this counterclockwise, for example, we can just ask our users use this clockwise one, or sometimes we may make even more free description. Why we have to have such kind of disconnected line? Just to introduce each edge without any appearance order and automatically detect the closed surface. That can be also a possibility. However, although this kind of description is quite much restricted, we should be very careful about their appearance order and rotation direction, but that will introduce some advantages in our implementation, so we will just stick to this file format. Okay? So now you have this kind of description about the shape or the closed surface we will consider. Okay, so you know what does it mean? This one is actually a test example of a cross section of a nanosheet. Usually nanosheet is represented as this kind of shape, rounded surface, and nanosheet wise or double gate wise plain flat part. So in this example I intentionally make this asymmetric situation. So here we have quite a right angle, and here we have a rounded angle. So just to show that this method can be applied to general cases. So usually we have a symmetric structure. Okay. So in this case, now let's try to assign the quantity called as level. How can we evaluate that level? So the level is corresponding to the distance. So the shortest distance from the boundary edges. So here, for example, let's think about a certain point. This is the point of our interest. We wanted to assign the level for this black dot point. Then what we have to do is just to calculate the distance between each edge. For example, between this and that, here we have a distance, and also this and that, we have this distance. This and that, we have a relatively short distance. Of course, we must calculate distance between this and that, this and that. Okay, all comparison should be done and take the shortest one. So what will be the shortest one? Of course, you can easily understand among them. So this one is corresponding to the shortest distance. So in this case, we say that, okay, the distance from the boundary is 2 nanometer. So first of all, you can develop a calculation routine to calculate the distance. So this one, so the right figure shown here just shows the result of that calculation. So what I have done is I just implemented a function takes the position, an arbitrary position. If an arbitrary position is specified, after that this function just to make the calculation of distance for each edge. Then take the smallest one. So by doing so, now we have this kind of behavior. So what does it mean? Actually, you can find that here we have quite a dark range here. This dark one is the values quite close to 0. Not exactly 0, because there is no guarantee that happen to be our point is corresponding to the exact boundary. So we may have the values close to 0. So this is corresponding to the one for boundaries. And here we have quite a high values. Okay, this is because here we have our nanosheet, and we are now talking about these points. And you know that the distance between these points are quite large, so we can see that steep increase of the distance, and yes, we can easily calculate this one. So what you have to do is calculate the distance. And now here we have already generated the level function. However, in this distance function, actually we don't have a negative value. For example, here we have a certain point, and here we have a certain point, and let's say that this point is the actual boundary. Here we have boundary. Then what will be the function, level function? So let's say that this is a quarter, and let's say this is a 3/4. Okay, this distance is 3/4, and this one is 1/4, and here we have a boundary. Then how can we get the information about this boundary point? I mean that. So maybe we can secure some spaces somewhere here. Okay. Now think about this one. There is a certain 2 points, and phi equal to 1/4, 3/4. Then please try to find out the boundary. Of course, you can easily guess that, okay, since this is a quarter and 3/4, and so maybe here we have boundary. But please, how about this? We can also think about this one. Boundary level is just always just positive, so we don't have any kind of boundary, because it doesn't have any sign. this is a positive number and this is a positive number. So there is no guarantee that, okay, when we have this kind of two positive number, in between them we have zero crossing point. Do you have a certain guarantee that if we have 2 points, they have the same point, same sign? And is there any guarantee that we have zero crossing point? Of course, it is possible, but also there can be a certain kind of possibility. But if we have different sign, then we can easily understand at least once the function should cross this horizontal line corresponding to the function value equal to 0. So simply speaking, as shown in this level set description, so since the boundary is defined as a level equal to 0, so instead of using just distance, but signed distance is prepared to implement this scheme. So simply speaking, if that is a point is inside the boundary, we want to assign negative sign to this distance, and if we have a point outside of this boundary, then we want to make such kind of a positive value. Then in this example, we can clearly we can clearly now see that, for example, this one becomes a positive half and this one becomes, for example, negative 3/4. Then we can find that, okay, there will be a certain zero crossing point and that will be the boundary, and which one is interior and which one is exterior of this boundary. So from their signs we can see that this negative part, this is interior and this is exterior of this closed surface. So please try to assign also sign. Then how can we decide whether a certain point is inside the closed surface or outside that closed surface? So fortunately we can easily check whether that is inside or outside. So convention, the sign convention is positive for an exterior point and negative level for an interior point. And what we can do is quite simple. Since we now have a certain surface counterclockwise rotating, now think about a certain point. Here we have a certain point. Is this in or out? So you know that this is of course inside the inside this surface. Then how can we check whether that is inside or outside? It is quite easy. Think about the vector corresponding to an edge, and also consider a vector corresponding to this testing point. Then please try to calculate cross product, not inner product, cross product between them. So cross product is corresponding to rotating from the first argument to the second argument, and their rotating axis is representing the value of our rotation. For example, in this case, what will happen? Now we are now talking about rotation of this into that, so you will find that the result corresponding to this positive g direction. So you will get positive value for your quantity. Okay, so between our test point, green point, and this blue one, we have a positive sign. Then let's think about the next edge. So how can you do that? So let me just do it together with you in this case. So now our blue lines go to here, and also think about our test point. Then please try to calculate cross product once again from here to there. We will have a rotation here, so once again we will have a positive value. Okay, so let's do it once again. Now for this direction, also we can make the cross product between this first vector and second vector, and also it will give us a positive value, and we can repeat till the end of this this is closed surface. And what we can expect is, okay, all of these cross product are positive. None of them is actually negative. Okay, so then maybe you can ask me, okay, I understand if we have an interior point, all the cross product becomes positive. Then how about the exterior points? If we have a certain point here, this is corresponding to an exterior point, then please try to calculate the cross product once again. For this one gives still positive value. Then maybe it is not certain to check the cross product. So let me just do it once again. This and that, still that gives us a positive. Well, and if we consider this one, this and that gives once again gives positive. But point is, for this last one, if we calculate the cross product, then we must calculate the cross product between this vector and another vector, and it gives the rotation from here to there, clockwise rotation. So that will give us -1. So simply speaking, so if your point is on interior point, actually, since our polygon is assigned in a counterclockwise manner, so always from the viewpoint of your line segment, your motion, you always have your point on your left hand side. So here, if this is a certain point, you always run this way, and when you are asked whether you have your target point in your left hand side or right hand side, you always say that, okay, it is always on my left side. If you are coming here, still you have left. And even in this case, your movement direction is here, and always left and left. However, if your point is somewhere here, then in some parts you will find that this one becomes just a right side point. So simply speaking, evaluating the cross product between your line segment vector and your test point simply gives you whether that is located in the left side or on right side, and the right, or left, that kind of constellation should be consistent when you have interior points. So please implement another function which can detect this quantity. So by performing it, we can now construct this one. So the difference between the previous one, this one just unsigned distance, and now I assign the sign problem if we have interior points, then just to multiply -1 to the distance. So now you have quite a smooth transition between our negative values to the positive value. So that is, this signed distance is called as level. Level for what? Level for our boundary surface. So now let's assume that you have the level function defined on your regular grid. In this case, I just used 1 nanometer by 1 nanometer grid for the description. Of course, this spacing is not universal. For example, you can introduce 0.5, 0.5 or 2, 2. Any kind of description can be applied, or you can even generalize it to the different scales like 1, 2 or 2, 1. But anyway, you can make this kind of a level. Then once you have level function, then how can we reconstruct the boundary? So eventually we must reconstruct the boundary for our later use. Then how can we do that? For each edge of the rectangular grid, please just to make an interpolation. So if, as we did in this case, if we have two different values, then please try to find out the zero crossing point, and that zero crossing point is found. So in this figure, you are now looking at two different ones. Here you can see lines. These lines, that is the one provided by user. User wanted to express the shape of our nanosheet using lines. And you can find dots. Dots are obtained from the level function. First, we constructed the level function, and by interpolating the zero crossing point, now we can find certain points. Once after getting this node, so now we can make the real final description by connecting these nodes. So that will give you certain form or certain surface expressed by the Leveson method. The point is, are they completely matched or not? So as you can see here, after connecting them, these lines, so you can actually see that there is a change of the actual boundary. Also, for example, here the user, although user shows a certain joint here, but that is now gone, and they are just connected in a straight line. Also, you can see that user wanted to have the right angle for this left side. However, from this one, you can just have a little bit graded shape shown here. Also, you have graded shape here. So simply speaking, I wanted to say that the Leveson method cannot exactly reproduce the shape, the original shape. Of course, there is a certain differences. Why do we have such kind of small differences? Because we have introduced the finite resolution for our rectangular grid. So here I have used 1 nanometer by 1 nanometer, but instead of that, let's say that I have introduced 1.1 nanometer by 0.1 nanometer. What is your expectation? Then we will have much fine resolution about the original surface. So simply speaking, although well, its ability to describe the boundary is still limited by its own mesh size, but anyway it can reasonably well describe our complex boundaries. Okay, so now let's wrap up today's lecture. Okay, today's lecture is quite simple. Please write the program which can perform the same capabilities I have shown up to now. So in this case, the user, you can provide a set of points, a separate file, text file, and from this text file, please calculate level set, and from this level set, so please draw x, y, comma level. It means that please try to evaluate or draw these graphs. Okay, then please test your program, your own program with your own cross section. Please do not just test only one single example shown here. It is not enough. Please try to do many ones and say that whether your reconstructed boundary by Leveson method closely follow your original intended boundary. Okay. Okay. Do you have any question about this Leveson method? Okay. So today's lecture is quite much limited about how can we actually calculate the level set out of the initial structure. Now we have the initial structure. Now we wanted to make a certain change of this boundary. So now instead of explicitly changing the mesh, now we will change the level set function little bit. Then that is implicitly means that the boundary has been changed. So we will do that job in the next lecture 21st. Okay, do you have any question? Nope. Then I would like to wrap up today's lecture a little bit earlier. Okay. Okay, thank you for your time.